Okay, so this video is for Physics Module 12 practice problems. So we'll just work through them, starting with number 1. Number 1 says that an object is placed 3.5 centimeters away from a concave spherical mirror whose radius of curvature is 5 centimeters. Draw a ray tracing to illustrate the image and then tell whether it's real or virtual, upright or inverted, magnified or reduced. Okay, so first of all, we are told that it is a concave mirror. So we'll draw it as a concave surface. We'll draw our line through the middle. And then we are told that the radius of curvature is 5 centimeters. So I'm just going to estimate. So this is actually let's make that a little bit farther away. So if the radius of curvature is 5, so that's R, that means that the focal point would be half of that, 2.5. And then the object is placed 3.5 centimeters. So we'll place that about right here. Okay, so then we are now ready to do our ray tracing. So the first rule tells us that if something goes in horizontally, it will reflect through the focal point. And then secondly, if it goes in through the focal point, it goes in through the focal point, when it hits that mirror, it will reflect out horizontally. So our point of intersection is right here. The lines actually did intersect, so it is a real image, so we didn't have to extrapolate anything out. This is the bottom, so that makes this the top. So it is inverted, and the image is magnified. Not a huge difference, but it definitely is bigger. This image is bigger than, so this image is bigger than that image, so it is magnified. Okay, so that is number 1, real, inverted, and magnified. Okay, number 2 is again a concave mirror. So we'll draw our concave mirror, draw our line through the middle. And now we are told that the radius of curvature is 10. So we'll put that at 10 centimeters, that's R. So that means the focal point would be half of that distance, that would be 5. And our object is placed 3 centimeters away. Okay, so here's our object, 3 centimeters. Scoot that back just a little bit. So we'll put our object right there. Okay, so now we see that we can't really draw a line through the focal point, but we can draw a line as if it went through the focal point. So we'll draw the red one first. Let's just make this a little bit smaller. Okay, so we can't draw it as if we can draw it as if it went through the focal point. So it would be this line here, okay, and it's going to reflect out horizontally after it hits the mirror, and then the other one will go in horizontally And when it goes in horizontally, then it will reflect through the focal point. Draw that like that. We see that these two lines, the red and the blue reflective lines, are not going to intersect, or intersect. So we will extrapolate this out like that. We'll extrapolate our red one out like that. We see that they intersect with each other right there. So this is the bottom, so this is the top, so it's upright. If we compare the size of this image to this one, it's magnified. And because we had to extrapolate the lines out, it is a virtual image. Okay, so that is number 2. Okay, number 3 states an object is placed 5 centimeters away from a convex spherical mirror. Okay, so now we've got a convex mirror, and the object is placed 5 centimeters away. So we'll just say this is the object here, and it says that the radius of curvature is 6. Okay, so remember this. So this would circle around like this, right? So the radius of curvature and the focal point are going to be on this side of the lens. Let's get rid of some of that. Okay, so the radius of curvature was 6, so that means we said that was 5, so we'll make this that's 5, we'll make this 6, so that's R, and so F is half of that at 3. Okay, so now we'll first go in horizontally. Okay, so it's going to go in horizontally, it's going to hit that mirror, and it's going to reflect out of the focal point. So it's going to reflect out like this. Okay, and then the next one will go in through the focal point. It's going to go in as if it were going to go through that focal point. It will hit the mirror on the way, and it will reflect out horizontally. Okay, we see they don't intersect, so we will extrapolate this out, and we'll extrapolate the red one out as well. So those two lines intersect right here. Okay, so first of all, because we had to extrapolate, we know it's a virtual image. So the object will look like it's coming from the other side of the mirror. So it's not a real image. This is the bottom, so this is the top. So it's upright. And if we look at the size, this is smaller than this. So it is reduced. Okay, that is number 3. Okay, number 4 tells us that light is traveling in air and is incident on a block of ice at an angle of 25. So that means that it says the angle of incidence is 25 degrees. What is the angle of reflection? Okay, so we know that the angle of, we know that the that N1, so the N, the index of reflection for the angle of incidence is a sine of the angle of incident is equal to the index of refraction for the sine of the angle of refraction. Okay, so what we are told on this is that, so it's traveling in air. We know that N1 for air is 1.00, and we're told that the angle is 25 degrees. So we'll take the sine of 25 degrees. That's going to equal N2, which we are given as 1.31, times the sine of theta 2. Okay, so we'll just divide both sides by 1.31. That gets rid of that on this side. So that 1 times the sine of 25 divided by 1.31 will give you 0.3251. So that is equal to the sine of the angle of refraction. So then if we take the inverse or shift of the angle, shift of the sine, that comes out that 19, with two significant figures, the angle of refraction will equal 19 degrees. Okay, we're going to skip number 25, or number 5. We're going to skip number 5 and go on to number 6. The index of refraction, so N for ethyl alcohol, is equal to 1.4. What is the speed of light in ethyl alcohol? Okay, so we know that N is equal to the speed of light in air divided by the speed of light in the substance that we are interested in. So we know the speed of light in air. We know this, so we're trying to solve for this. So let's multiply both sides times v. That gets rid of the v on this side. Divide both sides by n. So then v is equal to c divided by n. Okay, so v is equal to the speed of light in air, which is 3.0 times 10 to the 8 meters per second, divided by n, which we were given as 1.4. Okay, so the index of refraction has no units, so the units that we'll end up with are meters per second. And if we do that, you should get 2.1 times 10 to the 8 meters per second. So light will travel in ethanol at 2.8 times 10 to the 8 meters per second, so slower than in air. Okay, number 7. Okay, so number 7 tells us that light is traveling in a special kind of glass known as flint glass. If it encounters air at an angle of incidence of 20.1 and refracts at 35.7, what is the index of refraction of flint glass? Okay, so the index of refraction times the angle of incidence, which we are told the angle of incidence is 20.1, so it's the sine of 20.1, and that will equal the angle, the N2, which in this case is going to be air, and it's going to refract at an angle of 35.7, the sine of 35.7. Okay, so now we're just going to solve for n1. So we'll just divide both sides by the sine of 20.1. That gets rid of that on this side. So if you take the sine of 35.7 times 1, divide by the sine of 20.1, you should get that n1 is equal to, with I guess we can have three significant figures. And I only put down 2, so let's do this math again. So 35.7, the sine of that, divided by 20.1, the sine of that, equals. So it's actually comes out to 1.69. So I guess it would be 1.70 as our index of refraction for that flint glass. Okay, number 8. Now we're going to do problems that relate to a lens. The first two are on converging lenses, and the last two, or the last one, is a diverging lens. Okay, so number 8 says we have a converging lens. So let's go ahead and draw our lens. It's converging. And we'll draw our line down the middle and our line through the middle. Not in the middle. Okay, and then it says that it has focal points 12 centimeters from its center. Okay, so remember, a lens is going to have focal points on both sides of the lens. So we'll make, and we measure from the center here. So we'll make that one focal point, and then we'll try to get this one an equal distance. So that's okay. So once again, we're 12 centimeters out. So that's a focal point. And get our line down the middle. And we'll make this about the same distance as another focal point. And then we're told that the object is 3 centimeters from the lens. Okay, so we'll put our object right here. Okay, so this is a diverging or converging lens. So the a light beam that goes through the lens from the top of the object, and when it hits the center of the lens, then it's going to converge through the focal point. Okay, so it's going to be like that. And then if it comes through the focal point, it's going to go out horizontally. Okay, so it comes through this focal point, it's going to hit the center of the lens, and it's going to go out horizontally. Okay, we can see those two lines will not intersect, but if we extrapolate this line out and we extrapolate the red one that came through the focal point, so we just extend this out because it came through the focal point, those two will intersect right there. This is the bottom, so this is the top. So we would say it is upright. Comparing the size, this one is bigger than that one, so it's magnified. And it is virtual because we had to extrapolate the lines to get it. Okay, so that is a converging lens. The next one, number 9, is also a converging lens. So we have our converging lens. This more in the middle. Okay, so there's our converging lens. Draw a line down through the middle and through our middle that way. And now number 9 says the focal points are 8 centimeters away. So we'll say this is 8, that's a focal point. And then we'll try to make, measuring from the center, try to make this one about the same distance. You guys could be measuring them, actually measuring them. I'll do a better job of getting those equal. So let's draw a line through the middle. Okay, so the focal points are 8. So that's a focal point there. And we will eyeball it and put it about right there. And then we told our object is 12 centimeters, so it will be half this distance away. So it's going to be there. Okay, so we will draw our object there. Okay, so let's take our red line. Red one will go in horizontally, and it will converge through the focal point. And then the other one will go through the focal point. And when it reaches the center of the lens, it will go out horizontally. And it will intersect right here. So it's going to be off our board there a little bit. So this is the bottom, so this is the top. So our image is inverted. And it's a little hard to tell, but it is a real image because those lines will actually intersect with each other over here. And it's a little hard to tell, but it also will be magnified. And if you draw it more to scale than I did, you should see that it is magnified. Let me go ahead and do that one again. What I think I will do is let's do number 9 again. See if we can draw it a little bit better so that we can see. I'll move the lens over here a little bit better. Okay, so that goes through there. This is going to go through here. So our focal points were at 8. Okay, so we'll say this is an F, and this is F, and so then we'll put our object here at 12. Okay, so first of all, it's going to go in horizontally, and then it's going to converge through that focal point. And then secondly, it will go in through the focal point. Right there at the tip of the lens, and it will go out horizontally. That's better. So then we can see that those two lines intersect right here. So this is the bottom, so this is the top. So the image would be inverted. It's enlarged, so magnified, and it's a real image because the lines themselves intersect. We didn't have to extrapolate them at all. Okay, so that's number 9. Lastly, we have number 10. Number 10 is a diverging lens. So here's our diverging lens. Diverging lens, like that. And we'll put our line through the middle and through the middle this way. Now we're told that the focal points are 8. Okay, so we'll put a focal point there. Try to make this one about the same distance. Focal point there. Bring that out just a tad. There. And our other focal point there. And then the object is 5 centimeters. So if that's 8, we'll say this is 5, and that's where our object's going to be. Okay, so now, because it's a diverging lens, the red line will go in horizontally until so that beam of light hits the center of the lens, and then it is going to reflect, it's going to converge out as if it went through this focal point. So it'll converge out like this. Okay, and then the other line will go in. Oh, the other line is if it's going to go through that focal point over there. It's heading toward that focal point over there, and when it reaches the center of the line, it is going to diverge out horizontally. So again, we see those lines are not going to intersect with each other. So we will extrapolate this horizontal one out, and we will extrapolate the red one, the diverging one out, and we will see that they are going to intersect right here. Okay, so this is the bottom, so this is the top, so it would be drawn like that, so it's upright. It's clearly reduced. And because we had to extrapolate the lines out, it is virtual. Okay, so that's it for the practice problems for Module 12. on geometric optics.